This presentation will be all about vector spaces and subspaces. So first, let's try to understand real vector spaces. Vector spaces have three things in general. First are the objects. These objects can either belong or not belong to a set called S. Now, these sets can either be integers or even real numbers. And whether such an object belongs to a set or not would then be used to identify if a set is considered to be a vector space. Second, we have the operations. So we are familiar already with some arithmetic operations like addition, subtraction, multiplication, and division. However, in vector spaces, we are introduced to two types of operations which are customly defined. And this operator can be defined in any way we want it to be. And these are vector addition and scalar multiplication. Now, these two operations, although they are named as vector addition and scalar multiplication, may be defined in a different way that we are not familiar with. So maybe, like for example, in another universe, we can consider for example, in another universe, we can consider addition of two numbers to be just equal to let's say something like this. Or we can say that multiplication is subtraction in another universe. So we can define these operators depending on how we want them to be, which is another important thing in vector addition and scalar multiplication. They may not be defined as vector addition as we know it, which is adding two vectors element-wise, and scalar multiplication wherein we multiply a constant to a vector and apply that multiplication to each and every element. This may be different for every vector space that we will encounter later. Lastly, we have the properties. These properties involve the operations and the objects that were discussed a while ago. So let's say we have vector addition and two elements that belong to the set. We want to know if after applying such operation, that this result could belong to the set or may not belong to a set. Another thing to consider are the different types of properties. Like for example, in addition, we have associativity, commutativity, identity, and distributivity. And for vector spaces, we want to consider the question, do all the properties hold for all objects in the set under the given operations? And these properties that we will see later, there are 10 of them, and we would have to investigate each and every one of the properties with respect to the operations and objects in the set to consider something as a vector space. So to formally define a real vector space, we consider it as a set of V elements which has two operations defined with the following properties. So first, we have the closure of addition over here. So meaning, if we add two elements coming from the same set, the resulting element should also belong to the set. Followed by that would be, if an element belongs to the set and another element belongs to the set, for all elements, it is commutative in nature. Next is the associativity property, wherein adding two vectors or three vectors, regardless of which goes first, should give you the same result. Next, we have, for all elements coming from the set V, there is an existing element, which is the zero vector, wherein, regardless of how you add them together, should give you the original vector. So next, we have the negative of a vector. So for all elements U coming from the set V, there exists a negative U vector, wherein U, and applying the vector addition operator to negative U and U, regardless of which goes first, should give you the same answer, or which is the zero vector. Next, we have the closure property for scalar multiplication, which indicates that if such a vector belongs to the set and we have a scalar, which is a real number, it has to be a real number, applying the scalar multiplication operator should give you an element that belongs to the set. Next, we have the left distributivity of scalars. So here, we're actually distributing a scalar to two vectors, which should give you something like this, and it must be equivalent to both sides for all vectors u and v in the set V, and a scalar, which is a real number. Similarly, we're also applying another distributivity property here, but instead of distributing from the left, we are distributing from the right a vector. So this one is actually a vector, and we want to apply distributivity to both scalars and apply the vector addition operation to each and every when each and every vector which is multiplied by a scalar. Then we have for all elements u part of the set V, for all scalars c, and for all scalars d, which are both real numbers. It is similar to the associative property, wherein regardless of which one is applied first in scalar multiplication, it should give you the same result. Take note also that this multiplication refers to the arithmetic multiplication that we're all familiar with. Next is the identity property, wherein multiplying it by the scalar 1 should just give us the same original vector for all vectors u in the set V. So all in all, we have all these 10 properties discussed, and each of these need to be checked in order to consider a set to be a real vector space, provided our two operations right here. And to add some terminology, where the elements of V are considered to be vectors, these vectors may not be the vectors that we're familiar with, which is an n by 1 column rather. But vectors can be considered as functions, polynomials, and even matrices. So the concept of a vector should be extended not only to vectors that we're familiar as like one column or one row, but it can extend to even other kinds of mathematical structures, such as, again, functions and polynomials. The elements of real numbers are considered as the scalars. And then we also have operations, vector addition and scalar multiplication. And unique elements, this is important, the zero vector and the negative of a vector u. So examples of real vector spaces are the set Rn, or basically vectors, which are n by 1 in dimensions. And then we also have the set of m by n matrices, which is dictated by this notation over here. So now let's consider the theorem first before applying the exercises. So if V is considered to be a vector space, that is, we have all 10 properties are satisfied, then the following would then hold. For all elements coming from the set V, if we apply a scalar multiplication operation to a vector and the scalar u, 0, which is the 0 that we usually use, should give us the 0 vector. Then similarly, for all elements from the scalar or set of real numbers, multiplying the 0 vector to any scalar should give us the 0 vector. And these two are somewhat related to this one, wherein if we multiply a scalar and a vector and get the 0 vector, then that can either mean that the scalar is 0 or the vector is the 0 vector. Lastly, for all elements coming from the set V or the vector space, if we apply the scalar multiplication to the -1 scalar, that should give us the -u element. So let's try to these exercises. For this video, we will only tackle the first two items. So first, we need to identify if something is a vector space, or if the set, given the operations, are considered to be a vector space. So we consider, in this example, our set to be R squared, wherein we have two vectors, u and v, And we define the vector addition to be element-wise addition, which is the one that we're used to, or the standard vector addition. And then we have scalar multiplication to be defined as 0 and c times the second element of the vector u. So notice that this one is different or is defined differently than the scalar multiplication that we are familiar with, which is why it is also important to consider how the operations are defined. So let's try to investigate each and every property of this example. So first, we want to see and investigate on the closure property of vector addition. So here, if U is part of the vector of the set V, and so is the vector V, then it should also give us the same element. The result rather should be part of the set V. So if we have U1, which is our U, vector U, apply vector addition to another element, which is the vector V, we should get, based on the rule defined here, we add the elements together, giving us U1 plus V1 and U2 plus V2. So from here, we need to also investigate the nature of the elements for each vector. So in U here, this is said to be a set of real numbers, or R squared. This one is also a set of R2. And notice that the elements here are real numbers. So with that being said, if these are real numbers, then the result or the sum would be a real number. Similarly, for the second element, adding two real numbers gives us a real number, which means that the vector addition should give us an element that belongs to R2 or the set V. So with that, that means that we satisfy property 1. So let's try the next example. This time, it is the commutative property of vector addition. So again, we list down the rule over here. So this time, we want to investigate both sides of the property. So we add the two elements, like so. And then, we want to also investigate the other side, which is V plus U, since that is what we want to determine if doing the other way around should also give us the same answer. So V1, V2 first, and then U1, U2. So let's try to answer this. So again, following the rules that are provided here, we want to add them together. So U1 plus V1, U2 plus V2. Now here, since V1 goes first, we need to strictly follow the order in which it is defined. So if U goes first, then the element of U should go first. So similarly, since the element V goes first in the vector addition step here, when we add these two elements together, we need to make V1 go first, followed by U1. And then similarly, V2 goes first, then U2. Okay, so now that we're at this point, we want to check if it's commutative or not. So one thing to consider is, this one is already the arithmetic addition that we are familiar with. And from the addition that we're familiar with, or arithmetic addition, we know that adding two numbers is commutative. So since this one and this one are this one should show us that it is actually commutative since based from arithmetic addition, these two are equal. So we can simply like change the sequence of this vector and give us u1 plus v1, u2 plus v2, which is equal to our vector over here at the left-hand side of the equation, which means that these two are equal, so therefore, it is following the commutative property. So next, let's try to check on the associative property of vector addition. So similarly, we will write down each and every step again. So following the rule over here, we're in vector addition. Depending on which pair of numbers goes first or elements, we should still get the same answer. So this one is for this one. And then we want to also check the left-hand side of the equation. So u1, u2 in parentheses with v1, v2. And then apply the vector addition operation to w1, w2. Okay. So again, we simply follow the rules that are defined for vector addition. So let's do that real quick. So we will add it as follows depending on the sequence. And that should give us, for now, this result for the left-hand side of the equation. And for the right-hand side of the equation, that gives us u1 plus v1, u2 plus v2, and then the vector operation for vector addition and w1, w2. And then from there, we apply these two together and again, follow the same rules as provided in the definition of vector addition for this example. So we add them sequentially. So since vector u goes first, we add the element first of vector u, followed by the element in this vector v1 plus w1. So we write it like so. And then similarly for u2, v2, and w2, you add them sequentially as well. On the right-hand side, we also follow the same sequence in vector addition. So u1 plus v1 first, followed by w1, and then u2, v2, and then followed by w2. And since we got the equal answer here for both sides of the equation, that means that this one is associative. So far so good. We have already 3 out of the 10 to examine. So next, we have item number 4, which is on the 0 vector of R2, or this vector space, if it is a vector space. So we want to find some vector 0, which is the 0 vector, when we add them together, it gives us the same answer. Okay, so if this is our vector u, applying vector addition to, let's call this our 0 vector, z1, z2, should equal to u1, u2. And applying the vector addition operation here, when we add them together, that gives us u1 plus z1, u2 plus z2. So this is the result that we have so far. And now you can observe that we can actually like turn this into linear equations. So let's do it just that. So we're basically turning this into linear equations. So we turn it into like this form, like so. And then when we just apply algebra, we subtract both sides by u1 or u2, and that should give us z1 equals u1 minus u1, and z2 is equal to u2 minus u2. I notice that the results of both would give us 0. Therefore, a 0 vector exists for this set, and that 0 vector is actually 0, 0. So that is our 0 vector, and it exists. Therefore, we can consider this as part or satisfying the property of the 0 vector. So now that we're done with the 0 vector, we now investigate on the vector addition further by finding the negative vector of u. So let's go over that this time. So here, we want to look for the negative vector u. So we want to find the vector that, if we apply the operations, it gives us the 0 vector. And as mentioned a while ago, our 0 vector is said to be 0, 0. So for the negative u, let's define it to be x sub 1 and x sub 2. So this one is what we want to find out if a negative u exists in the vector space. So let's again turn this into linear equation. So u1 plus x1 is equal to 0. And u2 plus x sub 2 is equal to 0. What we want to find out is the value of x sub 1 and x sub 2. So we subtract again both sides of the equation with u sub 1 or u sub 2, which should give us x sub 1 equals 0 minus u sub 1. X sub 2 gives us 0 minus u sub 2. And our final answer there would be negative u sub 1 and negative u sub 2. Which means that a negative vector does exist, and that negative vector is defined to be negative u sub 1 and negative u sub 2. Which means we have satisfied the fifth property for vector addition. Next, we have this time the scalar multiplication properties. So we've now tackled all 5, and we have seen that it has satisfied all properties so far. So now we investigate further on the scalar multiplication properties. So we want to find out the closure property of scalar multiplication. So if we have a vector u and apply scalar multiplication to it with some scalar c, so let's add our c to the other side actually. So then that should give us an element that is part of the vector space. So following the rule of scalar multiplication rather, we need to strictly follow this rule, wherein the first element has to be 0, and the second element is the scalar c multiplied to the second element of the vector u. So we need to strictly follow this. So that gives us 0 and c times u sub 2. And then again, we investigate the properties of each and every element in the vector. So u sub 1 and u sub 2 again are part of R2, meaning all elements are part of the real numbers. And here 0 is a real number, and our scalar c is a real number, and our element u sub 2 is a real number as well. Meaning, if we multiply two real numbers, we get also a real number. Therefore, it is part of, it satisfies actually the closure property of scalar multiplication, because each and every element is a real number, and all in all, this vector is actually part of the R2 space or set V, as mentioned over here. So it satisfies property number 6. So far, we have already satisfied the closure property of scalar multiplication. Next is the left distributivity property. So in here, we want to investigate if multiplying or distributing the scalar to both vectors gives us the same answer. So again, applying the operations, so that gives us C. We can also write the scalar multiplication like this. So that gives us U sub 1, U sub 2, vector addition with V sub 1, V sub 2. And if that also gives us the same answer as C, scalar multiplication with U sub 1 and U sub 2, followed by vector addition of C and scalar multiplication of V sub 1 and V sub 2. So let's first handle the left-hand side of the equation. So in parentheses, this would give us, based on the definition of vector addition, U sub 1 plus V sub 1, U sub 2 plus V sub 2. Now, from there, we need to solve the right-hand side of the equation, starting off with scalar multiplication on both elements in the right-hand side. So, applying the rule on scalar multiplication, this one gives us, first, 0 and C times U sub 2. Then, apply vector addition to it, to the next element, 0, and then C times V sub 2. Then altogether, we apply scalar multiplication and vector addition to both sides of the equation. So let's start with the left-hand side. So applying scalar multiplication to this will give us 0, and then followed by C multiplied by U sub 2 and V sub 2. Followed by, for the right-hand side, we add them together like so. So this gives us 0 and C U sub 2 plus CV sub 2. Now notice that this side of the equation, C sub CU2 and CV2, is actually equal to distributing C to V2 and U2, which means that these two are equal actually. Therefore, it satisfies property number 7 of left distributivity of scalar multiplication. So, we've satisfied now 7 properties of the vector space. Next is the right distributivity of the vector. So in here, we are multiplying a vector U to both scalars, which is what we're trying to do for the next item. So again, following the rule, copying it, will give us U sub 1 and U sub 2 equals to C scalar multiplication of U sub 1 and U sub 2, followed by vector addition of D times U sub 1 and U sub 2. Okay, so from here, we apply first the left-hand side of the equation. So let's evaluate the left-hand side first. So when we apply scalar multiplication to this gives us 0, and let's make this wider. So 0, and then C plus D, our scalar, times U sub 2. For the left-hand side, this gives us C, and followed by, actually, this one is scalar multiplication. So 0 first, followed by C times the element U sub 2. Applying vector addition gives us then scalar multiplication of d and u sub 1 and u sub 2 gives us 0 and d u sub 2. And here, when we apply vector addition, we simply apply the rule like so. So this gives us 0, c u sub 2 plus d u sub 2. And then here, 0, c plus d u sub 2. So now, observe that c plus d, we can factor this out and give us u sub 2. This one would give us this result. We factor out the u sub 2 and give us what remains is the scalar c plus d. On the left hand side, we can see that this one is actually commutative because multiplying is commutative. Regardless of whichever comes first, you get the same answer. So technically, we can put u sub 2 first in multiplying before c plus d. And notice again that these two are equal. So therefore, we satisfy property number 8, or right distributivity of vectors. So we've satisfied already 8 properties and we have 2 more left to go. Next is property number 9, wherein for all vectors u and 2 scalars c and d, it is following similar to the associative property. So here we have c scalar multiplication of d scalar multiplication of u. And is that equal to cd, like arithmetic multiplication with the scalar multiplication of u sub 1 and u sub 2. Alright, so left-hand side of the equation, first again, we apply the rule of scalar multiplication to d and u, giving us d, first is 0, followed by d times u sub 2. Copy the c and the scalar multiplication. On the right-hand side, we already apply yung scalar multiplication operation. So that gives us 0, followed by cd times u sub 2. And then we again apply scalar multiplication to the left-hand side rather, giving us again 0, followed by c d u sub 2, which, as you can notice, is actually equal to the right-hand side. And because it's equal, that gives us the satisfiability of property number 9 of the associative property of scalar multiplication. So now we're down to one more property of the set, and that would be the identity property, wherein multiplying 1 with the vector should give us the same vector. So our vector is again u sub 1 and u sub 2. Followed by our scalar c, or 1 rather. So what we want to see is if 1 scalar multiplication of u sub 1 and u sub 2 should bring us back to the same answer. So when we apply the scalar multiplication rule, we get 0, and then applying the rule for the second element, it is 1 times u sub 2. Notice that it is actually not equal to our expected answer, which is u sub 1 and u sub 2. Because, as you can see here, 0 is not equal to u sub 1 for all the time. U sub 1 can be 0, but it can also be any other number. Therefore, since it does not satisfy this property, therefore, it is actually not satisfying this property. Therefore, although we have satisfied all 9 properties, if one property does not get satisfied, then therefore, this entire set and operations provided gives us that it is not a vector space. So, in evaluating vector spaces, you need to evaluate all 10 rules to identify whether it is a vector space or not. So here, this one is also another example of a vector space that we can evaluate. So when we mean by standard vector addition and standard multiplication, scalar multiplication, standard vector addition just basically means the scale vector addition that we are used to. So adding 2 vectors together is basically what it means to add 2 vectors. For scalar multiplication, we are basically multiplying a scalar to a vector and apply each or sort of broadcast this scalar to all elements in the vector. So that is what we mean by standard scalar multiplication. Another thing to consider is the set over here. We have the set xy, part of R2, where x is a non-negative number. So we also need to take that into account when we actually add these together, or when we use these in evaluating the properties. So usually when we evaluate vector spaces, the first things that you need to evaluate are these two, the closure properties of vector addition and scalar multiplication. So let's try to evaluate those first. So in actually evaluating first closure property of vector addition, we apply like so, which should give us, based on the rules that are provided, standard vector addition, we simply add them as is. Next, we investigate on the properties of each and every element. So u sub 1 and v sub 1 are both non-negative. So x is greater than or equal to 0. And u sub 2 and v sub 2 are just real numbers. And when we add them together, a non-negative number plus another non-negative number will always give us a non-negative number. And here, this one also gives us a real number, since both second elements are also real numbers. Therefore, we've satisfied the closure property of vector addition. Followed by, this time, the scalar multiplication property. So, multiplying a scalar to a vector should give us the result c u sub 1 and c u sub 2, since it is standard scalar multiplication. We then investigate the properties of the result. So u sub 1 is greater than or equal to 0. U sub 2 is part of the real numbers. However, observe that c, our scalar over here, is any real number, meaning c can be positive, negative, or even 0. And the fact that it can be a negative number means that cu sub 1, multiplying it with a negative number and a positive or zero number will give us only two results: a zero, a number that is zero, or a negative number if it is a negative and a positive number being multiplied together. So the fact that CU sub 1 can actually be negative actually violates not this part of the um, property, because our first element would then not be non-negative anymore, since our scalar can actually be negative. So it is actually not part of the vector set or the set V. Therefore, if it does not satisfy already that property, then it is also not a vector space. So some things to consider in evaluating vector spaces are the following. To be able to efficiently check each and every property, we first start off with the closure property. So this can be like a strategy in identifying the hierarchy of which is more important to evaluate first. So aside from these two first, we then evaluate the zero. Actually, before that is the commutative and associative properties, followed by the zero and negative u vectors. And then you can evaluate the other four however you would like. But this one is not supposed to be followed. It's merely a tip to help you in evaluating vector spaces faster. So now we proceed to the subspace. A subspace is defined to be a non-empty subset of the vector space, which is also applying the same operations that are part of the vector space V. And we also have another term called the trivial or the zero subspace, which is the set containing the zero vector. And it is also considered as the subspace for V. So, one important theorem is known to be the subspace test, which is given a non-empty subset of the vector space with respect to the operations vector addition and scalar multiplication, it can only be a subspace of V if and only if it follows the following conditions, wherein it also follows vector addition and scalar multiplication rules within the subset. Another thing to consider also is that in this theorem, you should also consider that 0 is part of the subspace. Because, as you can see a while ago, the 0 or the zeros vector is considered as a subspace with that only element in a set. So we need to also consider 0 as being part of the subspace in the test. So we have to consider 1, 2, and 3 things in identifying if a subset is considered to be a subspace of a vector space. So let's try to evaluate this example. Identify if it is a subspace. So our vector space is R3. This one is already a vector space. Then we want to consider if that subset ABC, where A plus 2B minus C is equal to 0. If it is a subspace or not. So first, we evaluate vector addition. So in vector addition, we basically add them together. So A sub 1, B sub 1, and C sub 1, vector addition of A sub 2, B sub 2, and C sub 2 should be equal to, and since this vector space also to add, when you have vector spaces that are Rn, or maybe the set of matrices of order Mn, these follow the standard vector addition, and scalar multiplication. So that is implied or assumed already. So when we add them together, that should give us a sub 1 plus a sub 2, b sub 1 plus b sub 2, and c sub 1 plus c sub 2. So from here, you may think that we are stuck, but we need to also consider the property of the subset, which is satisfying this equality. So first, we consider a sub 1 plus 2b sub 1 minus c sub 1 is equal to 0. And another property that should be true also is a sub 2 minus 2b sub 2 minus c sub 2 is equal to 0. Therefore, adding them together will give us a sub 1 plus a sub 2 plus 2b sub 1 plus 2b sub 2 minus c sub 1 minus c sub 2 equals to 0. Then we can actually group the elements together to have a clear picture of what exactly is going on. So we group them accordingly. So a sub 1 plus a sub 2 plus, we can factor out also the 2. So that gives us 2 times b sub 1 plus b sub 2. We can also factor out the negative, giving us negative c sub 1 plus c sub 2 equals 0. And from here, you can see that this actually represents your A, this represents your B, and this represents your C. Meaning, if we substitute these values with A, we substitute these for B, and we substitute these for C, it actually gives us the same equality over here, wherein A plus 2B minus C is equal to 0. Therefore, that should satisfy vector addition. So, we already have vector addition done. We check out now scalar multiplication. So, in scalar multiplication, again, multiplying any scalar of part of the real numbers with any vector ABC should give us CA, CB, CC. To make it less confusing, let's change the scalar to K instead. Alright, so from here, we again evaluate the property which is A plus 2B minus C. So, similarly, A, we'll just write this as A since it's only one vector. So, KA, or let's start off with A plus 2B minus C is equal to 0. And then, what we want is to substitute it with the resulting vector over here, which is KA plus KB, 2KB minus KC is equal to 0. We can actually factor out the constant K, or scalar K rather, and give us back the original equation. If we divide both sides by K, that gives us A plus 2B minus C equals 0. Which means that this actually is satisfying scalar multiplication because we have satisfied the property right over here. So that is done for scalar multiplication. One last thing to consider also is the zero vector. So, to check whether the zero vector exists, we then have to one thing you can do is actually to look on the properties of the given subset. So given a vector ABC, we can say that a plus 2b minus c is equal to 0 based on the property defined. If we replace all of these with 0, we should still satisfy the property. So that gives us 0 plus 2 times 0 minus 0 is equal to 0. And when you add them together, that gives us 0 equals 0. So we satisfy the property, therefore, the 0 vector actually exists in the subspace, or subset rather, which means that once we have applied all three properties, therefore the subset is actually considered to be a subspace. So let's have another example with regards to subspaces. So here, we this time have a matrix of 2 by 3 matrices. So again, we need to check also the vector addition, scalar multiplication, and the 0 vector. So first, we investigate on the vector addition. So here, we add them together. So this becomes a sub 1, b sub 1, c sub 1, d sub 1, e sub 1, f sub 1. Applying vector addition to another element. Should give us the property, or should give us the result a sub 1 plus a sub 2, b sub 1 plus b sub 2, c sub 1 plus c sub 2, d sub 1 plus d sub 2, e sub 1 plus e sub 2, f sub 1 plus f sub 2. So from here, we then apply the two properties that are mentioned here. A plus z is equal to 0, and b plus d plus f is equal to 0. So combining these, we have to apply to each and every matrix first before the result. So we have here a sub 1 plus c sub 1 is equal to 0, and b sub 1 plus d sub 1 plus f sub 1 is equal to 0, followed by a sub 2 plus c sub 2 is equal to 0, and b sub 2 plus d sub 2 plus f sub 2 is equal to 0. And what we are expecting is that a sub 1 plus e sub 2 plus c sub 1 plus c sub 2 is equal to 0, and the other equation, b sub 1 plus b sub 2 plus d sub 1 plus d sub 2 plus f sub 1 plus f sub 2 is equal to 0. So from here, we need to do something else to actually prove that it actually, or to prove or disprove whether it is part of vector or it satisfies vector addition or not. So here, we first rewrite the equation first. So a sub 1 plus a sub 2, c sub 1 plus c sub 2. We can actually rearrange the terms accordingly and give us a sub 1. So we'll group those that are coming from the same matrix. So a sub 2 and c sub 2. We can group these together because, again, it's commutative. It's just addition. So we can group them however we want. And then, notice that a sub 1 plus c sub 1 and a2 plus c sub 2 are both equal to 0. So we can substitute these for the equation and write down 0 plus 0. And true enough, it is equal to 0. Therefore, it satisfies one part of the vector addition that we are trying to verify. Similarly, when we group the elements accordingly for the second equation, that gives us b sub 1, b sub 1, and f sub 1 together, and then b sub 2, b sub 2, and f sub 2 together. And again, following the equations over here and over here, that gives us 0 plus 0 also, which is also 0. And therefore, we have satisfied both properties of the subset. Therefore, it satisfies vector addition. So let's now then consider scalar multiplication. So this time, we multiply a matrix, scalar k to the matrix A, B, C, D, E, F, giving us Ka, Kb, Kc, Kd, Ke, and Kf. So from here, we want to try to satisfy both properties again. So let's rewrite the properties of this one, or of this result. So that should give us Ka plus Kc equals 0. This is what we want to, we're trying to prove that it also follows the properties above. So similarly, Kd plus Kd plus Kf is equal to 0. We can factor out the k for both equations, giving us this result. And then, based from the properties, a plus z is equal to 0 and bd plus f is equal to 0. So we substitute these two with 0. So that gives us k times 0 is equal to 0 and k times 0 is equal to 0. So since both are equal to 0, it satisfies both properties since each equation was equal to 0. So therefore, it satisfies scalar multiplication. And lastly, we need to also evaluate if the 0 vector also exists. So again, given a matrix 0, 0, 0, 0, 0, 0, it should also satisfy the properties given above. So taking this 0 and this 0, which is the A and the C, it gives us 0. Then we take the B, the D, and the F, and it also gives us 0. Because again, this is actually the 0 vector for M, 2, 3. And notice that when we add this, try to satisfy the properties, we actually get 0, or they are equal, therefore the 0 vector exists. And not only that, since we've already verified vector addition and scalar multiplication, that gives us that this subset is actually a subspace of the set M23 or the set V. So that is the method in checking whether a subset is considered to be a subspace or not. You have to check each and every condition as well, and also take note of the properties of each and every or the properties that hold for the subset. So aside from equalities like this, you can also find properties such as A, like for example, A is greater than, like, let's say C, or can be the case that A plus B should be equal to C. So some similar things like that can also appear as properties of a subset. So that is all for vector spaces and subspaces. In the next video, we will discuss linear independence and spanning sets.